So I'm Akash. This is the virtual workshop for experimental design. We're basically just going to be going over, the rules, some difficult topics that you may be struggling with, some common questions that a lot of people have about the event, and some tips that I have for you guys and other free resources that you can use to prepare for the event. So in terms of the rules, if you're new to XD, like I guess a very simple way to describe it is that you basically have to make a science fair project in 50 minutes. And they give you a template with a bunch of different sections that you have to fill out. Uh, and that's outlined in the rules basically. For the most part, the template they have to fill out is very similar between Division B and Division C, but some of the main differences outlined here are that in Div C, you have to fill out a standard of comparison on the first page. And in Div C, in the rubric for the event, if you want to get full points, you have to do 4 Ivy levels instead of 3. And in Div C, they care about sig figs, and in Division B, they don't. And in Div C, you have to fill out an abstract, whereas you don't need to do that in Div B. Uh, so yeah, the biggest part of this event is uh, adhering to the rubric as well as possible. I think, yeah, so this is the rubric for Division C. This is something that you want to look at and basically memorize before you even go into the event, the day of the competition. And before I get to the rubric, I want to mention that they did add something new to the rulebook. Well, this line that I pasted here has always been there, but they added this part that says falsifying/making up fake data. So let me read it. Any team not collecting data by conducting an experiment on site or falsifying/making up fake data. So they added the part that I bolded here will have their score multiplied by 0.25. So basically, if you falsify data on your experiment, you're definitely not going to medal and your placing is going to go a lot down. So that's something you definitely want to avoid doing. I know in the past, a lot of teams that I saw at tournaments that I went to, especially invitationals, fake data and something specific I think a lot of teams did was they did an experiment where they only did one trial for each Ivy level, and then they came up with the data for the second and third trial in order to save time. And I don't know how easy it will be for judges or people supervising the event to figure out if people are, faking their experiments. But if they do, there is a high chance that you'd lose a lot of points. So something you want to consider when you're competing, that it is very risky doing so. And so this is the rubric. If you're new to the event, this is something, like I said before, you really want to have an understanding of. Um, Something that I like to do with my partners a lot is before every tournament, we come up with an outline of who's doing what section and we fill it out on the rubric itself. So this is just a random image that I took last year when I was in Science Olympiad doing XD. And it was basically for me and my partners to keep track of who was going to do what section at an invitational. So we have each person's initials here and yeah, it's a good way to make sure that you guys have an understanding of who's going to do what section. And yeah. So here's some difficult topics that you may need help in XD. It's some stuff that I especially struggled in when doing the event. Uh, this first topic isn't really a difficult topic, but it's something that it's basically a fundamental of XD that you need to know, even if you're not doing this section. So all these terms have to do with the first section, parts A, B, C, and D of experimental design. And even if you're not doing this section specifically, uh, you definitely need to know what these terms are when you're communicating with your partners, especially. So, a hypothesis is an educated guess or prediction about the relationship between the IV independent and DV dependent variables. And a basic format that I would definitely use is the if then because format for not hypothesis. I know there are other ways to write out your hypothesis, but this is definitely the simplest and it's the easiest way to format. Um, and that's the name of the game for XD. I know a lot of other teams that did the event tried to overcomplicate things when in reality, because there's such a concrete rubric that you're being graded on, you want to make the experiment as simple as possible and just stay as close to the rubric as you can. So yeah, independent variable, that's the variable you're changing in your experiment to see what effect it has on the dependent variable, which is the variable that you're measuring in order to see what changes when you alter the independent variable. And then something I know that when you're new to XD, it's kind of confusing the difference between controlled variable and constant. But basically, what controlled variable is, it's a variable that is possible to change. So it is possible for you to alter that variable, but it's the variable that you keep the same on purpose in order to make sure that your results are only being affected by the independent variable, which is a variable you're changing on purpose. And on the other hand, constant, that's something that cannot change because it's like a fundamental uh, like aspect of an environment. So the example I have here is that gravity is 9.8 meters per second squared. So if you're doing like a physics experiment, it's like impossible for the experimenter to change the value of gravity. But let's say you're doing an experiment where you're bouncing a ball from a certain height. You're releasing a ball from a certain height and measuring the rebound height, like how high it bounces in the air. Then a controlled variable for that uh could be the size of the ball or like the weight of the ball. If you Because it's possible to change those characteristics. It's possible to change, the size of the ball, use a different ball, or have different weighted balls. But in an experiment, you could keep that variable on the same on purpose in order to have the independent variable be something different, like the initial height of the ball in that experiment, for example. Topic two is significant figures. This is something that only matters in Division C. So if you're in Division B, this doesn't really have that much significance. I know when I was in high school, this is something we learned about in like chemistry class in like 10th grade. But at the same time, it was something that I kind of struggled with in XD. But as I did the event more, I gained more of an understanding. So basically, significant figures, it's a concept used to make sure that your data has the correct amount of decimal places uh, or significance of data. Uh, so to figure out how many significant figures are in a measurement, these are like the basic rules. So all non-zero numbers kind of significant figures. So if there's a digit 1 through 9 in a number, then that's definitely a significant figure. So like in 4009, in that number, 4 is a significant figure and 9 is a significant figure because those numbers are non-zero. And if a 0 is placed between significant figures, so the 0 is placed between the 4 and the 9, those have to be significant according to this rule. And the last rule is that if you have a 0 placed after a decimal point and a non-zero number, then those zeros are significant. So in this number 4.00, these two zeros are significant because they're placed after a 4. But if you have 0.0400, the 0 that comes before the 4 is not significant because it comes out, even though it comes after a decimal place, the decimal place comes after a 0. So I know this is very confusing, but if you want to gain a concrete understanding, here's a link that I have here that basically takes you to SciOly Wiki, which is a very useful resource, and it goes more in depth about, this concept. Um, but yeah, that's basically how significant figures work. Um, there is a concept called pure numbers where you're dealing with like whole number of objects. So like let's say you're counting how many eggs are in a basket. You can't have like a decimal number of eggs. So you can only have 12, you can only have like 11, 12, 13 eggs. You can't have a decimal amount like 12.5 or something. And for those types of numbers, uh, they have an infinite number of significant figures, is what is generally said about them. And that's useful when you're doing calculations like addition and subtraction and multiplication and division. And that's why significant figures are so important in XD. So when it comes to addition and subtraction, uh, the rules in terms of significant figures are basically the result will have as many decimal places as the number with the least is the number that you're adding or subtracting with the least decimal places. So in this example I have here, since uh, the number with the least decimal places out of these four numbers is 4.1, which goes to the tenths place. When you get your result, you're going to round that result to the tenths place. So we got a result of 42.694. Since 4.1 is the number with the least decimal places, we round to the tenths place, so we round up to 42.7. And then for multiplication and division, when you're uh, multiplying or dividing two numbers, the answer will have the same number of significant figures as the number with the least number of significant figures that you're multiplying or dividing. So in this example, 2.10 that has three significant figures and 3.607 that has four significant figures. So if you multiply those two numbers, you get the result. And when you're rounding that answer, since you want to round it so that you end up with three significant figures. So we round 7.5747 to 7.57 because that's three significant figures, and the number with the least in our initial two numbers was 2.10, which is also 3. So the application you'd use this for in experimental design is especially for the statistics section. And I can go back to the rubric if you want a refresher, but basically the statistics section, that's where you write down, stuff like the mean, median, mode, standard deviation, min, max, range, stuff like that. Uh, so in this example I have here, this is an example I took directly from an XD experiment that I did in the past, and it basically says, is basically for the mean. And when I'm calculating the mean, I have three trials of data, and I'm adding the three numbers together from those three trials and dividing them by 3 to find the mean. So each of these numbers, they're all to the hundredths place. So that means my answer also has to go to the hundredths place based on the rule for addition and subtraction. And when you're dividing by 3, some of you may be thinking that, oh, since this number has one significant figure, then shouldn't you round your result to 1 instead of 1.13? The reason you don't do that is because this 3 is a pure number. So like we said in the previous slide, a pure number has an infinite number of significant figures. It's basically like a whole number, whole value that you don't it's impossible to have a decimal amount because this 3 represents the number of values that you're taking the mean of. So you can't have a decimal amount for that, so it has infinite significant figures. And this statement here is from the XD scoring explanation doc, and this is a really useful resource that I'll talk about later that basically defines how judges or event supervisors are going to grade your experiment and your template. And it says about significant figures that all data reported using the proper number of significant figures for the tool of measurement used. And basically, what that means is it doesn't really matter that all your data points that you take when you're doing your experiment or have the same number of significant figures. What matters the most is that your values reflect the measurement tool that you're using. So I'll get into that in the next slide. This is like a sample experiment that I took. I think this experiment is from an invitational that I took like 2 years ago. And it does have some mistakes in it in this data table. So basically what the experiment was is we changed the temperature of corn syrup. So that's the independent variable. That's the value that we're changing. And we saw the effect that had on the amount of corn syrup that dripped out of a container in a matter of 30 seconds. So when we did this experiment, we had tools that basically looked like this. So we had a digital scale and we had a thermometer. So this thermometer, it reads to the each line here, each small line represents 1 degree Celsius. And we use Celsius over Fahrenheit because that's, the metric system. In the scientific world, you definitely want to stick to using metric system as much as you can. So in this experiment, in this thermometer, the Celsius is measured by increments of 1. So 0, 1, 2, 3, 4, 5, and so on. And we wrote down the temperature of corn syrup to the tenths place. And you're able to do this because, especially in chemistry, what they tell you and in experimental design in general is if you have an analog measuring tool that has like lines like this, the maximum precision you can measure to is 1 decimal place above the lines that are used. So uh, basically, even though this thermometer can measure to the ones place, you can approximate the decimal point to the tenths place between if the measurement is between two of the lines. So this is correct in the data table. These values 11.7, 16.3, 20.0. And then these are the dependent variable results. The which we measured using the digital scale. And the thing that we did wrong is when the mass exceeded 10 grams, we got rid of one significant figure. So instead of saying like 10.93, we rounded it to 10.9 because we wanted to keep the data at 3 significant figures. But based off of this scoring explanation doc, we need to report data using the proper number of significant figures for the tool of measurement. So since this digital scale measures to the hundredths place, all of these data points should also be measured to the hundredths place. So that is a mistake that we lost points for in this experiment, is that instead of saying like 10.93, we rounded to 10.9. So that's something you don't want to do. You want to make sure that all of your data points reflect the measurement of the tool you're using. So remember, for analog tools, you can measure 1 decimal place above the increments that are, or the lines that are written here. And for a digital scale or some sort of digital measurement tool, you just copy the number that's on the tool. And this is another example of statistics, and it has a few mistakes in terms of significant figures that I want to go over. So this is physics-related experiment where we had to figure out the effect of a mass of a rigid body, that the mass of a rigid body has on like the period of rotation, basically. And what we use to measure period, which is a unit of time, is basically a stopwatch. And this was a digital stopwatch that measured to the hundredths place. So because the stopwatch measured to the hundredths place, you want to make sure that all of your results for your statistics also are to the hundredths place. So when I measured mean, I had thousands place for some values and stuff like that, and that would cause me to lose points for significant figures because the stopwatch can only measure to the hundredths place. So instead of writing 0.836 here, I would instead write like 0.84 to round to the hundredths place. And for standard deviation, instead of saying like 0.0206, I'd round to 0.02 so that all the data points are to the hundredths place. And this is completely unrelated from significant figures, but this is a tool that I use for specifically the statistics section and the quantitative data section in experimental design. So basically, I had a TI Inspire, and I made a table uh, where I could just like fill in the values for the three trials for all four of my IVs, and it would spit out basically all the things that I would need for statistics and quantitative data, like mean, median, min, max, range, standard deviation, uh, and like the line of best fit and stuff like that. And this is something I think at the end of the presentation, I have a link to this automation tool that you can use. You can download it from Google Drive and you can upload it to your calculator if you have a TI Inspire. So if you don't have a TI Inspire, it won't work. But you can replicate something similar to this in your own calculator. It's pretty easy. Third topic that I'm going to be going over is CR template. I don't know how it works in Georgia, but in Pennsylvania, the the CR kind of changes from the national rubric, which I have on the top right. So in Pennsylvania, instead of doing variation, outliers, and data trend, they did like precision and something else. So but in terms of like invitationals and the national tournament, it's pretty much gonna CR is pretty much gonna look like this. Uh, so yeah, the three CRs that you're gonna do are variation, outliers, and data trend. And something that my partners and I did a lot in high school was we just had a basic template for each of these three CRs. And whenever we were competing in an invitational, we stuck to that same template and uh, just like replaced values based on what the experiment was. Um, so for variation, the template that we did was basically we looked at how the variation of each data set for each IV changed as you increase the independent variable. So the reason that a lot of the time we had a trend for this, and it was something that we could do for CR, is because when you increase the IV for a lot of experiments, especially in physics, the precision of your results is gonna decrease a lot of the time. Like your data is gonna get more spread out as you increase the IV because usually when you increase the IV, it causes your experiment to become a lot more chaotic. So this is a template for variation. As the IV increased, the variation for each data set for each IV increased or decreased. You would change this whether on based on what the trend is. And for evidence, we used the standard deviation for each IV. And for reasoning, something that a lot of teams do for reasoning is they give like a scientific reason for why it's happening. Like they would, for this example, they would say, uh, the standard deviation increased because the because by increasing the IV, by increasing the initial height of the ball, you create uh, you create a more chaotic environment for when the ball bounces off the ground, and the imperfections in the ground would cause the ball to rebound in more chaotic movements, causing, more spread out data. And if you look at the CR framework, or not the, if you look at the experimental design scoring explanation doc, uh, it actually says that you don't need to do this. The only thing you need to do for reasoning is uh wait, let me actually pull up the scoring explanation doc so you guys can look at it because it's a very useful tool, not just for CR but for all the sections to get an understanding of what the ESs and judges are looking for when they're grading your experiment. So for if I go to CER, it says for reasoning, the author ties the claim together with the evidence to draw a conclusion. The claim is now supported with evidence, and the author completes the connection of the evidence in support of the claim. The conclusions developed through this process are data-driven and evidence-supported statements. So basically, they just want you to provide reasoning that connects the evidence to the claim. They don't require you to give some scientific reason as to why the claim is occurring. And it saves a lot of time because you don't have to provide the scientific reasoning. Something that our team did was I remember some of the times in previous invitationals, judges kind of misgraded our experiment because they were looking for us to provide a scientific reasoning for CER. And if we had extra time, we would give a scientific reasoning for each CR just to be safe. But most of the time, if you have good yeses and you have good judges at an invitational, they're not gonna dock points off for reasoning if you don't provide like scientific explanation for everything. So yeah. For variation, this is the reasoning that would be necessary. You could just say the standard deviation of each data set increases or decreases as the IV increases. Since the standard deviation indicates how far data points are typically from the mean, this increase in standard deviation indicates that the data points are becoming more spread out. Therefore, the increase in IV is increasing the variability of each data set. And then for outliers, it says in the scoring explanation guide that uh, you have to use a quantitative measurement for evidence. And one example that they provide in the scoring explanation guide is using the 1.5 IQR rule. So when when my partners and I made a template for outliers that we would use in an invitational, we just stuck with using the 1.5 IQR rule. And if you look at the automation thing that I made for the TI Inspire, I basically had the section for lower bound and upper bound, and it basically calculated the 1.5 IQR rule. So it took quartile 1 and subtracted it by 1.5 times the IQR for each uh for each IV. And basically what I did for CR outliers is I looked at each of the trials for each IV, and I made sure that all of these trials were within the lower bound and upper bound for uh, that IV. So, for example, for IV1, in this sample experiment, these three trials, 1.12, 1.34, and 1.27, all three of these values fall within the range of 0.79 to 1.67. So that would mean that there are no outliers for this IV. And the same applies for IV2 because all three of these values fall within this range, and then IV3 and IV4. So there would be no outliers in this experiment because um, all the data points fall within the lower bound and upper bound for their respective IV. So yeah, if you have no outliers, uh, then you'd say since all the data points fall within the range of the lower bound and upper bound, there are no outliers in the data based on a 1.5 IQR rule. And for evidence, you would just provide the lower bound and upper bound. And what I used to do is I would make a table, and the tables had columns labeled as IV levels, lower bound and upper bound. And I would just write down the lower bound and upper bound for each IV. And I would also just provide the formula that I used to find the lower bound and upper bound. And I mentioned that I was using the 1.5 IQR rule. So that's something you could do as well when you're doing CR for outliers. And for data trend, I'd say this is definitely the simplest IV. So one tip I definitely give for you is if you're short on time and you still need to do CR, start data trend first because it's the easiest to write. It's the shortest amount of stuff that you need to write. So the claim that I always used to do for data trend is I'd say that there's a positive or negative correlation between the DV and the IV, and I'd explicitly mention what the DV and IV are. And for evidence, I'd use the line of best fit. In the past, I used to use I literally used to write out the means for each IV, but that's definitely a lot more time consuming than just writing the line of best fit. And I know it may seem weird to simply just write the line of best fit for your evidence because it looks really like it looks like a small amount of evidence, but it's definitely sufficient for you to get the 2 points for evidence. And something that I would definitely consider is writing as little as possible when you need to write as little as possible in XD because it saves you a lot of time to look over your experiment and focus on, making sure that you adhere to everything in the rubric. And then for reasoning, I would say since the slope of the line of best fit is, and then I would insert what the slope is, which is, and then I'd mention whether that slope is positive or negative, and then I'd say the dv increases or decreases as the IV increases. So if the slope is positive, then the dv would increase as the IV increases. And if the slope is negative, then the dv would decrease as the IV increases. And then I'd say, therefore, there's a positive or negative correlation between the dv and IV. So those are all three topics. And I want to put everything together by basically showing you guys a sample experiment. And something that I used to do to practice for XD a lot is you come up with a sample experiment that you could do with a given topic and list of materials and try to come up with a experiment that you can do given that topic and set of materials. So this topic, oscillation of a pendulum, this is a really common topic that I've seen a lot of invitationals. It's a very simple topic, and it's very easy to do. So things that you have are string, hooked masses, meter stick, protractor, digital scale, masking tape, stopwatch, lab period, a lab table, and scissors. And the first thing I would consider when having this topic of oscillation of a pendulum is measuring the period of a pendulum. So basically that's the time it takes for the pendulum to swing back and forth once. So if you deviate the pendulum by like a small angle and then let go, the pendulum is obviously going to swing back and forth. So for your experiment, you could measure how long it takes for the pendulum to swing back and forth once. So that would definitely be the dv I would do for that experiment. And for the IV, if you don't have a good understanding of physics, you may be tempted to look at these masses and think of making your IV the mass of the hook of the pendulum. So basically, you would change out the mass for uh, based on what for different IV levels. So maybe you'd use a 10 gram max and hook it up to the pendulum and measure what the period is, and then do the same for 20, 30, and 40 grams. But the reason that this isn't a good experiment to do is because the mass of a pendulum actually doesn't affect its period. So basically, regardless of what mass your pendulum is, the period would not change and it would have a negligible effect. And the reason that this would be a bad experiment to do is it's very hard to come up with stuff for CER and for conclusion uh, if your data has no clear correlation or trend. So that for that reason, instead of doing the mass of the pendulum for my IV, I would do the length of the pendulum because that actually does have an effect on the period or how long it takes for the pendulum to swing back and forth. So yeah, so this is my sample experiment that I came up with. The problem I came up with was how does the length of a pendulum affect its period? And for the IV, it's obviously going to be the length of the pendulum measured from the axis of rotation to the bottom of the hooked mass attached to the string. And whenever you're writing down IV, so let me pull up the template actually so you can get an understanding of what it's going to look like when you're writing all this down in an invitational. So student report form, that's what you use, or that's what the ESs or event supervisors are going to provide to you when you're doing your experiment. So this is the template that you're going to be writing down coming up with your experiment. So in this section for independent variable, I would write down first. I would write down the units that you're using to measure your IV. Then I would write down the IV levels. So for IV level 1, I'd write 0.10 meters, point 0.2 for, and then 0.20 meters, 0.30 meters, 0.40 meters. And yeah, you would also want to write the tool that you're using to measure your IV as well. And that's the stuff that I typically write down when I'm filling out this section, this IV section in the reporting packet. And then for DV, the first thing you want to do is you want to define what the DV is. It's the average period of a pendulum or time it takes for the pendulum to oscillate back and forth once. And then I'd mention what the units of measurement are, which are seconds, and I'd mention what tool you're using to measure that DV, which in this case is a stopwatch. And then I'd also mention any additional calculations or definitions that you would need to use for an experiment. So in this case, this is just a specific example that I would use. A lot of the time when our team in high school did a pendulum experiment, we actually had raw data of 10 periods. So we would measure 10 periods of a pendulum. So we'd let the pendulum swing back and forth 10 times, and that's the value that we would record for one trial. And then, in order to convert that raw data into condensed data, we would divide that 10 periods time by 10 in order to get the time it takes for one period of a pendulum. So the average period, basically. And yeah, for controlled variables, uh, here are the controlled variables that I came up with. And something you want to keep in mind for controlled variables is that you want to make sure that the things that you come up with actually have an impact on the experiment if you didn't keep them the same. So for example, the angle that the pendulum is released from relative to its resting position. So if you change the angle that you release the pendulum from, it would have an effect on the period of the pendulum, like a small effect. If I wrote for controlled variables like the color of the string, that would not be a good controlled variable, and I could risk losing points because the color of the string of the pendulum is not going to affect its period. That's like a characteristic that doesn't have a significant impact on your data. So another controlled variable that I came up with is the mass of the object that is attached to the pendulum. I know I said earlier that this doesn't have an impact on the period, but it is a significant characteristic that does affect, you know, uh, like the force weight and like the physics behind calculating a value. So that is a decent controlled variable to come up with, even though it doesn't have a significant impact on, like the period of the pendulum itself. And then another controlled variable I came up with was the thickness of the string that the hook mass is attached to. This is probably the weakest controlled variable that I came up with out of these three, but I think it would have an impact on the period if you change the thickness of the string. But the thing is, these three controlled variables, even though it is possible to change them, in this sample experiment, these are characteristics that I'm going to keep the same. So for all of my trials, I'm always going to release the pendulum from 45-degree angle. I'm always going to use a 50-gram hook mass, and I'm always going to use the same thickness string. And then a good constant to use for this experiment is gravity. And this is something I definitely suggest in general is if your experiment is physics related, your best bet to put for constant is definitely gravity most of the time. Even if you're not dropping an object or you're like throwing a projectile. Let's say your experiment is like sliding uh sliding a a a ball or like rolling a ball across a table. Gravity still does have an impact on that experiment because it affects the weight of the ball. like it's what gives the ball weight, and it also affects like the normal force if you have taken physics between like the ball and the surface it's rolling on. So gravity is always a good bet to use for any physics related experiment. And for the hypothesis, I use the same if then because format that I talked about earlier. So my hypothesis was if the length of a pendulum, and I said in meters increases, the average period or time for one oscillation of the pendulum in seconds would increase because the period of a pendulum is determined by the formula T equals 2 pi square root L over G. And increasing L, the length of the pendulum, would also lead to an increase in T, which is the period. So yeah, I for the if part of the hypothesis, I mentioned the IV, which is the length of the pendulum. Uh, and then for the then part of the hypothesis, I mentioned the dV, and then I mentioned in the because part why uh, an increase in the length of the pendulum would lead to an increase in the period. And this because part is where you want to actually give like a scientific reasoning as to why you think something is happening. And then for standard of comparison, uh, yeah. So standard of comparison is something you would only do in Division C. If you're in Division B, uh, uh, it's not something that you would need to fill out in your reporting packet. And I think I forgot to mention it earlier when I was in topic one, but the standard of comparison is basically the baseline condition in an experiment that serves as a reference point to compare the effects of the independent variable on the dependent variable. So for this sample experiment, our four IV levels are 0.1 meter, 0.2 meters, 0.3 meters, and 0.4 meters for the length of the pendulum. So our standard of comparison would have to be one of these IV levels. And I chose the length 0.1 meters because every other IV level, 0.2, 0.3, 0.4, is a multiple of that value. So you can multiply 0.1 by 2, 3, and 4 to get these other IV levels. And I said, therefore, by using 0.1 meters as the baseline, it will be easier to observe how proportional increases in length. So basically, multiplying this baseline value in order to get other values increases. So, how proportional increases in the length of the pendulum affect the period of oscillation and recognize the exact type of trend of the data. So in this experiment, it wasn't really easy to come up with the standard of comparison, but a lot of in its chemistry experiments, especially, it's definitely a lot easier. And in a lot of experiments, you can literally use the value 0 as an IV level, and that would serve as a good standard of comparison. So an example that I can come up with at the top of my head is if you're doing an experiment about density where you have a cup of water and you're adding salt to that water and seeing how the amount of mass of salt that you're adding to the water affects its density. A good standard of comparison you can do for that experiment is having an IV level of 0 grams of salt. So you don't add any salt to the solution, and that would be a good baseline because it tells you the baseline density of the water without adding any salt to it. So that's the type of stuff that you can think of or come up with when you're uh, doing an experiment and coming up with the SOC or standard of comparison. And yeah, here's some general XD topics. Basically, I looked at a lot of previous XD experiments I did. I wrote down what XD topics came up a lot. And something that you can notice is a lot of the experiments that I have here are physics related. And the reason for that is an invitational is especially, it's a lot easier to find and gather materials for a physics experiment compared to like a chemistry experiment where you're doing like reactions and complex stuff like that. So something I definitely recommend when you're preparing for XD is to reflect how the number of physics experiments is a large portion of what you're going to see at invitationals and tournaments. So definitely try to practice with physics experiments a significant amount in comparison to chemistry and miscellaneous experiments. And for chemistry experiments, I would say that maybe at like college invitationals, like invitationals hosted by colleges like Penn State and Georgia Tech and stuff like that, I would definitely expect it to be more likely to see a chemistry experiment in comparison to like an experiment run by, a high school or something like that. Because those colleges have a lot more access to chemistry labs and like chemistry materials that you can use for an XD experiment. So yeah, that's something to keep in mind. And these are the list of common XD topics that you can see. Like I said before, pendulum shows up a lot. Um, Elasticity shows up a lot. Diffusion shows up a lot. Uh, yeah. And you can look at the SciOly test exchange. I have the link here. And if you go here and you press Control F and you search up experimental design, you can find uh, basic experiments that other people came up with that you can use to practice. And if you just search up SciOly test exchange and click the test exchange archive, this is also another link that's really useful because it has uh, experiments from specific tournaments as well. So those are some resources you can use to find experiments that you can do for experimental design to prepare and practice. And yeah, some tips that I have is to remember to bring your own ruler, stopwatch, and goggles to the event. This is because in the experimental designs rulebook, they say that you're allowed to bring these three materials, and a lot of the time, uh, uh, the event supervisor is not going to provide these materials for you. Some of the time, they're nice and they can give you like a ruler or stopwatch if you don't have it, but you definitely want to make sure that you have those materials on hand before going to the tournament. And goggles, if you don't wear goggles, then they won't allow you to compete a lot of the time if the experiment is like a chemistry experiment or something that you need lab safety for. And then something else that I would give a tip for experimental design is coming up with some automated statistics tool that you have on your calculator that automatically calculates mean, median, mode, standard deviation, and line of best fit for you. Like I said, I have my own automated tool for TI Inspire that you can download yourself, which I have at the additional resources section with this link. And you can upload it to your calculator using, the same cable that you use to charge your calculator. But if you have the TI-84, you can also make an automated statistics tool on your own. It's not that difficult. Something else to keep in mind is that you want to make your experiment as simple as possible to save time. So you don't. The reason I'm saying this is because as long as you adhere to the topic and as long as you adhere to the topic, basically, you're not going to get a penalty or lose any points for having a really simple experiment. Like I remember at the state competition, our experiment was literally um, a few years ago. It was if you add ice to water, then the temperature of water would decrease. That was basically our hypothesis. And that's a really simple hypothesis, and that's like common sense, basically. Like, of course, if you add ice to water, then its temperature is going to decrease. But because our experiment was so simple in that sense, uh, because we knew beforehand that the temperature is going to decrease if you add uh, ice to a solution of water, uh, we were able to finish our experiment really early and make sure that our entire packet was very detailed and it basically saved a lot of time for us. And at I think at that state competition we ended up medaling and we did really well at the competition. So it just goes to show that even if you have a simple experiment at a tournament, it's still it's actually the ideal in terms of what you want to do when you're competing. Something else that I would recommend is that you don't use all of the materials unless you is that you don't need to use all the materials that they provide you unless specified by the event supervisor. So yeah, you don't need to use all the materials you have. Something else is you want to make sure that your IV is quantifiable. What I mean by that is you want your independent variable, your IV levels, to be some sort of number. Like in the pendulum experiment, uh, the IV was the length of the pendulum. So it was like a number value. The reason you want to make sure that your IV is quantifiable is that it ensures that you don't lose points in sections like graph and stuff like that, where you are basically forced to make a line graph if you want to get full points. Um, so yeah, if you want to ensure that you get a full score in the test or get as many points as possible, make sure that your IV is a specific number. And if you want to medal in XD, you definitely want to ensure that you fill out the whole packet. I don't know if this is true for all tournaments, but for the majority of tournaments that I was in, all of the teams that medaled finished basically the entire packet. Some of the times they may have missed like one section in CR or like one small part, but for the majority of the time, the entire packet was basically filled out for all the medaling teams. So that should be a priority for you especially. And for data, do three trials for each IV level. That's basically a given. And for Div C, don't do 4 IV levels if the experiment is time consuming. I know I said earlier when I pointed out the rubric that in Division C, it basically says you in wait, it says yeah, levels of IV given. Since it's worth 4 points, how judges usually grade this section is if you only use 3 IV levels instead of 4, you'd lose 1 point for that part. But the thing is, that's the only point that you would lose in the entire rubric if you did that. So even though you lose 1 point if you do 3 IV levels instead of 4, it does save you a lot of time because you don't need to record as much data. So I would say if you have an experiment that is really time consuming and it takes a long time to record data for it, then it's fine to do 3 IV levels instead of 4 in order to save time and make sure that you're able to finish the whole packet and spend more time just ensuring that you get full points on other sections. And yeah, I know I pointed out some of these resources before. Let me go over some of the stuff that's useful in each of those resources. So the first resource I have is the official Science Olympiad website, and they have a list of their own resources here that you can use. Like I said before, some of the most important resources are the reporting packet, and this is a packet that judges are going to provide to you at the invitational for you to fill out. So yeah, this is something that you can print out on your own when you're practicing and doing your own sample experiments. Something else that's really useful is the scoring explanation guide. And like I said before, this document literally provides uh, descriptions of what ESs and judges are looking for when they're grading your experiment. Something else that's important is the checklist. Yeah, this is like the rubric that judges use as well to grade your experiment. And yeah, those are the main resources. There's some other resources that are here if you want to look at that as well. The SciOly wiki is also another really good resource. It basically outlines the basics of the event and the type of stuff you want to know. Basically the fundamentals of XD. So if you're new to the event, you haven't done XD before, then this is definitely the first thing you want to take a look at. Calculator automation. This is the thing that I showed earlier. This is what I used to do automated statistics on a TI Inspire. This is a TNS file. If you want to upload this to your calculator, basically what you can do, you can click the download button here, and then that would basically download the file. And in order to upload it to your calculator, you plug in your calculator to your laptop, and you use the TI Inspire student software. So you can search up TI Inspire student software, and it's basically this first link or the second link, and you can click download here, and you can uh, download it to your laptop, and you can use that to upload the file to your calculator. And yeah, those are pretty much all the resources. Thank you guys for coming. I guess I can ask you, if you guys have any questions, I can answer them now. I see some stuff in the chat. I can go over it. Someone asked, what does it mean in the rubric CV is correctly identified and relevant? What do you need to say about relevance? So for controlled variable, oh yeah, I think I mentioned this for the sample experiment. So like I said before, for the sample experiment, the controlled variable needs to be something that actually has an impact on the dependent variable. So if you say like color of the string for the pendulum experiment, that would not be a relevant controlled variable because it doesn't have an impact on the dependent variable, and it's not related to the physics behind the experiment. Uh, so yeah, that's the answer to that question. For a physics experiment, what would be another good constant to use apart from gravity? Uh, that's a good question. Uh, some other good constants. I know in physics class they told me about the universal gravitational constant, and I guess that is also related to gravity, but that's something else you could think of. What's for the person who asked that? What's like a experiment that you are thinking of that you couldn't use gravity for as like a constant? I guess I can come back to that later, but with friction, um, something with friction. I guess even in that type of experiment, you can still use gravity because if you think about the physics behind it, uh, friction is impacted by the by the weight force of an object. So wait, let me pull up paint real quick. So I think I learned in AP Physics that if you have like a block that's sliding across a surface, the friction that that block experiences, so the force of friction, is equal to the coefficient of friction multiplied by the normal force. And the normal force is equal to uh, a lot of the times the normal force is equal to some form of m times g, where g is gravity. So even in that experiment, gravity would still be a good constant to use. I don't think you'd lose points for it. Another thing for friction, I guess you could use is this, the static coefficient of friction. But in some cases, when I use that constant as a constant for friction-related experiment, the judges still took off points for that constant because this value can change depending on what surface this like block is being uh uh like this block is sliding across. So if the block is sliding across like sandpaper instead of like a granite surface, like a granite countertop, then this static coefficient of friction would change. So that wouldn't be a good constant. But yeah, even in a friction-related experiment, I feel like gravity would still work. Yeah. So other Q&As. What about the recommendation section? Any tips for that? Uh, that's a section that I definitely feel like our team struggled a lot with. It was tough to come up with recommendations for really obscure experiments. Something that I would recommend you doing is, especially with this list of common experiments that I have here, look at that and come up with uh recommendations that you can do for those experiments or even applications. That's something that our team did a lot to prepare for XD. Um, Someone else asked, can you go back to common experiments? Actually, let me just give you guys the link to the presentation right now so you can look at it, and uh you can also like click on the links and the other resources. So if you want to look at the experiment, here's a link. Or sorry, if you want to look at the slideshow, here's a link. Put it in chat. Uh, does anyone else have any other questions? Uh, I guess if nobody else has any other questions, that's all I have for the workshop. I hope you guys, learned something new that you didn't know before about XD. And if you have a TI Inspired, definitely feel free to use the, what's it called? The automated tool that I provided. So yeah, that's it. That's all I have. Thank you guys for coming. Yeah.
Thank you so much, Akash.